Hello teachers, welcome back to Chapter 4. We're going to talk about Section 4-3 today, Greatest Common Divisor and Least Common Multiple. When you finish this section, we should be able to understand and explain the greatest common divisor and least common multiple of two or more whole numbers by using a variety of methods. Applications of the greatest common divisor and least common multiple to word problems and their solutions, and the Euclidean algorithm for finding the greatest common divisor. So what is the greatest common divisor? Well, let's lead in with an example. Two bands are to be combined to march in a parade. A 24-member band will march behind a 30-member band. The combined bands must have the same number of columns. Each column must be the same size. What is the greatest number of columns in which they can march? So you have to imagine how we might do this. We need, again, the same number of columns. Now, it won't be the same number of rows, obviously, because we have a 24-member band and a 30-member band, but we want them to line up nicely to march in the parade. The bands could each march in 2 columns, and we would have the same number of columns. But this does not satisfy the condition of having the greatest number of columns. So we could have, again, just skinny down the middle of the road, 2 columns, but we want the greatest number of columns to fill the width of the road. It says the number of columns must divide both 24 and 30. So we need a number that divides into both 24 and 30. So first of all, let's just think of this on paper by hand. So what are the divisors of 24? Let's just list the divisors of 24. We know 1 times 24, 2 times 12, 3 times 8, 4 times 6, and then 5 doesn't divide into 24. 6 would be the next number, but we already have included 6. So our divisors of 24 are 1, 24, 2, 12, 3, 8, 4, 6. Let's do the same thing for 30. Okay, so 1 times 30, 2 times 15, 3 times 10, 4 doesn't divide 30, 5 does, 5 times 6, and then the next number would be 6, which notice we already have included here. Now I need the largest number that's on both of these lists, and notice 6 is on the 24 list and 6 is on the 30 list. So if we had 6 columns, would this not work out? Let's read on to see what we have here. It says the numbers that divide both 24 and 30 are 1, 2, 3, and 6. So if I go back to my list, why didn't they list all of them? Because we're trying to find what's common, right? And the values that are common to both of these are 1 is on both lists, 2 is on both lists, 3 is on both lists, 4 is on 24 list, but 5 is on the 30 divisor list, and then 6. So that's why they listed 1, 2, 3, and 6, whereas 6 is definitely the largest. So numbers that divide both 24 and 30 are 1, 2, 3, 4, 5, 6. The greatest of these, again, that we found is 6. And that brings us to the answer. The first band would have 6 columns with 4 members in each column, right? Because remember, there were 24 members in that band. And the second band would have 6 columns also, because we want the 2 bands to line up, but with 5 members in each column, because there were 30 members of the band. And that brings us to a definition. The greatest common divisor, or abbreviated as GCD to represent greatest common divisor, or the greatest common factor, both of those represent the same mathematical idea, of two whole numbers A and B, not both 0, is the greatest whole number that divides both A and B. Now, one method for finding the greatest common divisor is to look at rods. So, for instance, we have the 6 rod and the 8 rod. And what we're trying to do is divide these rods into equal parts of the same size. So the 6 rod can be divided with 3 2-unit rods, and the 8 rod can be divided with 4 2-unit rods, which means 2 rods could be the greatest common divisor. Now, if we could divide 6 up with something even larger, we could divide it in half with 3 rods, but the 8 rod couldn't be divided with 3 rods. And this list kind of summarizes what we just said. The 3 rods can be used to build the 6 rod, but not the 8 rod. On the other hand, 4 rods can be used to build the 8 rod, but not the 6 rod. The 5 rods can be used to build neither. And so you're just trying to find the largest number that will split up each of your values, and it has to work for both of them. Therefore, the greatest common divisor of 6 and 8 is 2. The rod method is a visual that I think is great to introduce students to this idea, but it doesn't work great for work that you do in your head. On the other hand, the intersection method, which we're going to talk about next, still doesn't necessarily work great in your head, but you don't have to draw pictures. You just need to make a list. So if you list all the members of the set of whole number divisors of the 2 numbers, then find the set of all the common divisors, and finally pick the greatest element in that set. And this is exactly what we did when we did the band problem, where we had a 24-member band and a 30-member band. We listed all of the divisors of each of those numbers and pick the largest number that was on both lists. So for instance, to find the greatest common divisor of 20 and 32, denote the sets of the divisors of 20 and 32 by D20 and D32. If we were to do this by hand, let's write that down. So D20. Now let's think about all of the numbers that divide into 20, or that divide 20, which are the divisors. So 1 divides 20, 2 divides 20, 3 doesn't, right? 4 divides 20, 5 divides 20, 6, 7, and 8 do not, 9 doesn't, 10 divides 20, and then finally 20 divides 20. And you could pair these up. Again, these go together, 1 times 20, right? 2 times 10, 4 times 5. Let's do the same thing for 32. So the divisors of 32 are, watch this, I'm going to do back to front. So 1 times 32. Next would be 2 times 16. Does 3 go into 32? It doesn't, right? Because 3 plus 2 is 5. 4 divides into 32 8 times. 5 does not divide 32. 6 does not divide 32. 7 does not divide 32. And I'm already up to 8. So I have this big gap in the middle. Is that okay? Sure it is. I just would scooch these over to make a neat set. Now, what is the largest number that is on both lists? And I think you probably see it. It is 4. 4 is the largest number that divides both 20 and 32. Now, I'm going to show you the typed up version just so you see it again. So there's the list for the divisors of 20, and then we have the list for the divisors of 32, which matches our list. And then notice common divisors. We have arrows here. So 1 is a common divisor, 2 is a common divisor, 4 is a common divisor. But the largest of these, and there's the intersection method, where again the largest of these common divisors is 4, and that's an easy way to handle this. Although sometimes when you're dealing with enormous numbers, instead of 20 and 32, you have 36,245. You might want to approach this a different way, but making a list is a solid way of getting the job done. But if you have really big numbers to deal with, I'm a big fan of the prime factorization method. So to find the greatest common divisor of 2 or more non-zero whole numbers, first find the prime factorizations. You remember the factor tree? Or you could use the box method that we did in a previous section, but find the prime factorizations for both of the numbers, and then identify each common prime factor of the given numbers. Very important there. It says the greatest common divisor is the product of the common factors, each raised to the lowest power of that prime that occurs in any of these prime factorizations. The numbers such as 4 and 9, whose greatest common divisor is 1, are said to be relatively prime. So again, if your greatest common divisor is 1, then the numbers are relatively prime. So let's do a few of these examples. So you see, we want to find the greatest common divisor of 108 and 72. So remember, there's two ways we could do this. We could use the factor tree. So I need two numbers that multiply to be 108. You probably recall your 12 multiplication facts. 12 times 9 is 108. That's not the only way to get there. 12 breaks down into 4 times 3. 9 breaks down into 3 times 3. Remember, we circle the branches that end with prime numbers, but 4 breaks down into 2 times 2. So it has to be all prime numbers, which means 108 has a prime factorization of 2 to the second power times 3 to the third power. And I'll refer back to that in just a minute. Now let's take a look at 72. 72, you might think about as 9 times 8. 9 breaks down into 3 times 3. 8 breaks down into 4 times 2. Of course, 3 and 2 are prime numbers, but 4 breaks down again. And if I write the prime factorization for 72, I have 2 to the third times 3 to the second power. Now the rules are, remember what it said, you need each prime factor the lowest number of times that for the exponent. Okay, so 2 shows up twice, or 2 squared. Here 2 shows up 3 times, or 2 to the third. The lowest of those is 2 to the second. The 3's, you have 3 to the third for 108. I have 3 to the second for 72. So I need the lowest of those, which is 3 to the second. So we could say our greatest common divisor for 108, 72 is 2 to the second times 3 to the second, which is actually 4 times 9, or 36. 36 divides 108, and 36 divides 72. So that's the handwritten version. And then, of course, I have you a typed version. You can just check our work real quick. Again, 180, that should read 108. So just now I'm noticing the error here. So 108 is 2 squared, which is 4, times 3 to the third is 27. 4 times 27 is 108. 72 is 2 to the third times 3 squared. That's what we got. And then the greatest common divisor of 108 and 72, again, this should read 108. There was a typo. Is 2 squared times 3 squared. Again, the lowest. So again, recap. 2 squared versus 2 to the third. You use the lowest of the two. 3 to the third versus 3 squared. We use the lowest of the two. And then when you multiply those together, you get 36. Next example, how about the greatest common divisor for 0 and 13? Now, this might seem like an unusual problem to you, the greatest common divisor of 0 and 13. Let's think about the divisors of 0. So what numbers divide 0? Well, you know what? All numbers divide 0 except 0. So all whole numbers divide 0 except 0. Remember, what we can't have is a 0 in front of that division sign. So you could just say A divides 0. Anything divides 0, just not 0. Well, what divides 13? Well, 13 just breaks down into 1 and 13. And again, 0 breaks down into any number that's not equal to 0. So what's the largest of the two of those? 13. So the greatest common divisor between 0 and 13 is actually 13. And we have a rule that says the greatest common divisor between 0 and any other number is that other number. And there it is typed up, but that didn't make it so very clear. So I wanted to make sure you understood that. So again, all numbers divide 0, just not 0. All right, have another example. What is the greatest common divisor of x and y if x is defined for us? So I'm going to highlight this. X is 2 to the third times 7 squared times 11 times 13. And y is defined to be 2 times 7 to the third times 13 times 7. I think I'm even going to go the extra step of just writing these right on top of each other. So 2 to the third times 7 squared times 11 times 13. Should we multiply all that out? Absolutely not. This is already prime factored for us. We do not need to multiply that out. Those are large numbers. Do we care? Not really. So the greatest common divisor of x and y, where x is defined to be above, is, now remember we look at each number that's in common. So first of all, let's figure out what's in common. So we have 2 to the third and we have 2 to the first. So we want to use the smaller exponent of those. So 2 to the first is smaller than 2 to the third. We have a 7 squared, and we both have 7s in common. We have a 7 squared with x and a 7 to the third with y, so we want to use 7 squared, the lowest of the exponents. There's not 11 in common, so we don't use it at all. There is a 13 in common. They're both to the first power, so I'm just going to highlight the one of them, and they do not have a 17 in common. So when I write this result, it's going to be 2 times 7 squared times 13, and we can multiply that out. 2 times 49 times 13, and I'm sure we'll see what that equals in just a minute. Okay, so again, has to be common to both of your factorizations, and you take the number to the lowest power that it appears in either factorization. Okay, so here we go. 2 times 7 squared times 13, there's the answer, 1,274. Here's example D. I want you to pause it real quick. You work this one out on your own, and let's see if we get the same result. But notice there are 3 x, y, z, but the story is the same. Okay, so you need values that are common to all 3 factorizations, and you need that number to the lowest power that it shows up in either of the 3 factorizations. All right, hopefully that problem worked well for you. So I advise lining these things up where you can see them a little better. So x is 2 to the third times 7 squared times 11 times 13. Y is 2 times 7 to the third times 13, times 17, and z is equal to 2 to the second times 7. Now we are only allowed to use factors that are common to all 3. So I do notice that 2, I'm going to highlight all 3 of them, 2 is common to all 3 of these. But we need the lowest exponent. So I'm going to use this 2 to the first that I have highlighted in green. Okay, so once again, 7 is common to all 3 factorizations. I have to use the lowest power. So 7 to the first. Anything else common? Now at first look, 11 certainly is not common. 13 shows up in 2 of them, but again, and not in Z. And 17 only shows up in Y. So what I have highlighted in green, that's going to be our greatest common divisor, or greatest common factor for X, Y, and Z, which is going to be 2 to the first times 7 to the first, which is 14. Now the typed up version of that, here you go, 2 times 7 is 14. And here's an E problem for you. Again, worth pausing, doing this E on your own, and then come back and see if we get the same result. So when I write the greatest common divisor And it is not necessary that you line these up if I use proper notation for x, y is equal to. So let's compare. I have a 5 to the 4th for x. I don't have a 5 at all for y. I have a 13 to the 10th for x. I don't have a 13 for y. On the other hand, I got a 3 to the 10th. No 3's over here. No 11's over here. There are no common divisors. Does that mean it doesn't have a greatest common divisor? No, it has one. It's 1. You remember what that's called? Relatively prime. And there's the result right there, because x and y have no common prime factors. The greatest common divisor for x, y is equal to 1. And they are relatively prime. Now, there is a calculator method to do this. I looked on my standard TI-30X that I tend to use for my courses, and this button is not on a TI-30X, but if you see something like this on your calculator, you may want to play around with it. Notice it has an SIMP key that can be used to find the greatest common divisors of two numbers. So you would press 120-180, then that SIMP equals, and it says it's going to give you this display, and then it keeps going, and then it says by pressing the X loop button, we see 2 on the display as a common divisor of 120 and 180. We know that's not the greatest common divisor. Then you loop again, and we see 2 again as a factor, and you keep repeating the process to see 3 and 5, and all the other common divisors. Finally, you're going to get to 60, and that would be your greatest common divisor. Again, I'm just going through this just in case you use a calculator with that. It is possible with certain calculators. Now, I want to talk about the Euclidean algorithm method. This is a very interesting method. It says if A and B are any whole numbers with B not equal to 0 and A is bigger than B, so keep that in mind, that's important. A must be bigger than B. Then the greatest common divisor for A and B is also equal to the greatest common divisor for R and B, where R is the remainder. So finding the greatest common divisor of two numbers repeatedly using the theorem above until the remainder is 0 is called the Euclidean algorithm. So very interesting concept. Here we go. So if we have positive numbers A and B, and A is not equal to B, it says divide the larger number by the smaller number. Makes sense. Is the remainder 0? No? Then divide last divisor by the remainder. If the remainder is 0, then the last divisor is the greatest common divisor of A and B. So let's see this example in action. So we're supposed to find the greatest common divisor for 10,764 and 2,300. And let me remind you, greatest common divisor, the ways we've done this, we did this with rods. Remember, that's good for visual examples, probably not good for big numbers. We did the listing method where we found the intersection of all common divisors and we took the largest. We did prime factorization, by far my favorite method, but the Euclidean algorithm is a good way to go as well, especially if you're dealing with large numbers. So notice what we did. We're taking the largest of the two, and that goes underneath the division bar, and then we're dividing by 2,300. Okay, so we got a quotient of 4, but the 1,564, that's not a remainder of 0, right? So the remainder, notice, goes out front now, and your divisor turns into your dividend, and you divide again. Okay, now notice the remainder now is 736. Again, the remainder is not 0, so what are we going to do? We're going to put that remainder, 736, out front, and the divisor is going to turn into the dividend. So this is the next line. So again, this is the line we just looked at, by the way. The 736 now goes out front, and the divisor turns into the dividend, and we divide again. Notice the 92 goes out front, the divisor turns into the dividend, and look, we have a 0 remainder. Okay. Now, what is our greatest common divisor? So you do all that work and then it's hard to even tell what the answer is. Notice it is the last remainder that we have, or the way they describe that in the directions is your last divisor. So let's don't look at the last remainder. Let's focus on the last divisor using the directions that they gave. The greatest common divisor for those two numbers is 92. Now here's something to think about. It says we're supposed to find the greatest common divisor of 134,791, 6,341, and 6,339. Now it goes on to say that any common divisor of three numbers is also a common divisor for any two of them. Now why would it say that? Because let's just focus on two of them. The greatest common divisor of three numbers cannot be greater than the greatest common divisor of any of the two numbers. So if any of the two numbers has a low common divisor, then this other number over here, the other one that you're not looking at, cannot have a greatest common divisor any larger than that. So they pulled a cute little trick here. Let's just focus on the greatest common divisor for these two numbers. So that's what we did here, the greatest common divisor of 6,341 and 6,339. Now what are they doing next? Notice they subtracted these two. Okay, now we got to think about why they did that. This goes back to the Euclidean algorithm. Let me scroll back for you and show you this highlighted part. The greatest common divisor of A and B, as long as A is bigger than B, is equal to the greatest common divisor of R and B. Remember, R is the remainder. Okay, so we come back over here. The remainder, if I divide 6,339 into 6,341, my remainder is going to be 2. That's where that 2 came from. They wrote it as a subtraction problem, but I'm really thinking about it as a division problem. Is 6,339 divides into 6,341 one time, and that's going to give us a remainder of 2. The subtraction they did is this part right here. So, the greatest common divisor of 2 and 6,339. Now remind yourself, why did I do that? So we did the remainder. If I go back to the Euclidean algorithm, is the same as the greatest common divisor of the remainder and B. B is the smaller number, or the second number. So that's where we are. B is the 6,339. Now, they could only possibly have 1 and 2 in common, but we know that 6,339 is not divisible by 2, right? Because it's an odd number. So again, this is odd. Therefore, 1 is the greatest common divisor for 2 of these numbers. You know what? You throw another number in the mix, and because the greatest common divisor can't be any bigger than it is for 2 of them, then the greatest common divisor is equal to 1. So that was quite the problem to think through. But if you can determine easily the greatest common divisor between 2 of the numbers, then when you throw that third one in the mix, it can't be any bigger than those 2. So when you're trying to pick 2 out, the most restrictive, maybe even the closer together the numbers, the easier it'll be because you can use that Euclidean algorithm. Now here's another interesting problem, very closely based on the last problem we did to wrap up this video. Then we'll come back for part 2 and talk about the least common multiple. But the greatest common divisor, the greatest common factor, remember we can use those terms interchangeably, of any 2 consecutive whole numbers. So we're saying numbers right next to each other. So again, an example, the greatest common divisor of the numbers 111, 112. That's what they mean by consecutive whole numbers. So, notice the first thing that happened here, let's highlight, they just wrote down what we're doing, and they changed the order. Is that okay? They put the n plus 1 first and the n next. Well, sure, that's fine, right? It doesn't matter which one you put first. But the reason they put the bigger one in +1 first is so we could use the Euclidean algorithm. Now, remember the last problem that we did where they just subtracted down here the greatest common divisor of 6,341 minus 6,339. They subtracted to get 2, but we talked about why they subtracted. Because really they divided 6,339 into 6,341. It went one time, and the remainder was 2. So that's what they're doing here. They subtracted the bigger one minus the smaller one, but really that's the remainder, 1, and then the second one. Now what do 1 and whatever number have in common as greatest common factors? Well, 1, because remember, our greatest common factor can't be, our greatest common divisor can't be any larger than either of the two numbers. So the greatest common divisor is 1, and we have proven that the greatest common divisor of any two consecutive whole numbers is 1. So right here, this is equal to 1. Any numbers that are right next to each other, the greatest common divisor absolutely must be 1. Now I'm going to wrap this video up. Please let me know if you have any questions about greatest common divisor or greatest common factor. And for part 2, like I reminded you, we're going to come back and talk about the least common multiple for numbers. Have a great day.